Hello, everyone. Welcome to Chapter 1 of Linear Algebra. In this chapter, we're going to study matrices. And matrices are simply speaking boxes of numbers. So we're going to simply introduce them, the terminology, the notation, and then we're going to study together operations that we can do to them. For example, when are two matrices equal? How can you add or subtract matrices? Can you multiply matrix by numbers? Can you multiply matrices? All these operations are going to be defined and introduced, and we're going to look at some examples together. So let's go. First section, let's look at some definition and notation. So what is a matrix? Well, a matrix is simply a rectangular array of numbers. So roughly speaking, a big rectangle with numbers in it. The numbers in the box are called the entries. Also, sometimes we use the word components of the matrix, but typically we use components more when we use vectors in mathematics. Because a matrix is a box of numbers, we want to be able to describe the size of that box. So the size of a matrix is described in terms of rows and columns. Roughly speaking, the rows are like the horizontal structure of your box, and the columns are the vertical structure of your box. So a matrix with m rows and n columns is going to be called a m by n matrix. If your matrix has only one column, this matrix is going to be called a column matrix or a column vector. So when we do study vectors as matrices, typically we put these vectors as column vectors. And if you have a matrix with only one row, this is called a row matrix. Let's go look at some example. First, let's look at this matrix A. Matrix A is a 3 by 2 because there's three rows, 1, 2, 3, and there's also two columns. So always the row number first, so 3, and then the column number 2. So the matrix A is a 3 by 2 matrix. Now, the next example, matrix B. Matrix B is an example of a row matrix because matrix B has only one row. If you count the number of columns, there's 1, 2, 3, 4. So matrix B is a 1 by 4 row matrix. Next on the list, matrix C. We can see that matrix C has 1, 2, 3 rows and also 1, 2, 3 columns. So this matrix is a 3 by 3. And when a matrix has the same number of rows and columns, that's an example of a square matrix. Our last example is matrix D. Matrix D is an example of a column matrix because there's only one column. If you are counting the number of rows in that column matrix, we have 1, 2 rows. So this matrix is a 2 by 1. And again, this matrix is an example of a column matrix. Now let's move on to some notation. So when we refer to matrices, when we are writing definitions or making computations, typically we use capital letters for matrices. Like here we have the big fat matrix A and the big fat matrix C, and I'm using capital letters for that matrix. And when we are talking about the components or the entries of that matrix, if we are using general numbers, we're going to use lowercase letters. Like here in the matrix C, we have the entries to be A, B, and C, D, and F. So these are the components which are numbers. So when we're using numerical quantities in general, we use lowercase letters. Also, when we talk about the numbers inside a matrix or just numbers in general, this is just a terminology that I'm going to state as a definition. But in a matrix, when we're talking about numeral quantities, typically we will refer them as scalars. But if I am using the word scalars as I'm talking about some random computation, I'm talking about some of those numbers inside the matrix. Next up is some notation. So if we are talking about a general matrix and we call it big A, so capital A, and we want to talk about the entries in that matrix, we're going to be using a lowercase a for those entries, but we want to be able to specify where they are inside that matrix. And we're going to be using the row and the column to refer to their position. So if you have an entry on the ith row and the jth column, we're going to write that entry as small a ij, or if there's no confusion for size and we don't need the comma, we're going to simply be using aij. So the letter aij, small lowercase a, means the entry of the big matrix A on the ith row jth column. For example, if we want to talk about a general 3 by 4 matrix, we would use the following notation. So we use a big capital letter for A, and if you look at all the entries in this matrix, I'm using a lowercase a for every single entry, but I'm using the subindex to really locate which entry I'm talking about. For example, if I want to talk about the entry on the second row, third column, I'm talking about the entry where the subindex is to 3. Like here we go. Boom. Okay, so that is the entry on the second row, third column. So A sub to 3. So the 2 is for the row number and the 3 is for the column number. So the general notation for a matrix with m rows and n columns, big A, will simply be a big box with a lot of little letters that are going to be indexed by that general number of rows and columns. So here you can notice that the first subindex goes from 1 to m, and this happens in every single column for that matrix A, where we have m rows. And now if you're looking at the index for the column number, they go from 1 to and end up at n because there's n column in that matrix. So this is the favorite notation for a general m by n matrix. There are other popular notation for general m by n matrix. It could be using square brackets with aij inside that square bracket, where I is going to be an index that is going to range from 1 to m, and j is going to be that other index that is going to range between 1 and n. Or we also have that notation, just a box, square brackets with aij when it's clear what the dimensions are. But I would say for us, typically all our examples are going to have like fixed dimension. So we don't have to worry too much about that notation. It's mostly used when we introduce a new definition or a new operation and we want to write things in general. But one set of notation that we already use in this video, if we talk about the set of all matrices with m rows and n columns, where the entries of that matrix, so what's in the box, are numbers, so real numbers, we're going to be using big M with those like fancy double column m by n. So when you see big M and you see the sub index, like in this case here, the sub index, we have m and then n. So we're talking about all matrices with m rows and n columns, and the big R in there here just means that we're dealing with real entries, or the entries in the matrix are real numbers. Last definition of this section that I already introduced earlier in my previous example is the notion of a square matrix. So a square matrix, A is just a matrix where the number of rows and the number of columns are the same. So if we have an n by n matrix, we have a square matrix. Sometimes we specify the order or the size of that matrix. So if you have a matrix which has like 4 rows and 4 columns, we say that the order of that matrix is 4. And if you are dealing with a square matrix, there's some special entries that we call the entries on the main diagonal. And these entries are A11, A22, and ANN. So those are the important entries that are called the diagonal entries of the matrix. For example, here we have a matrix A, and that matrix A has 4 rows and also 4 columns. So this matrix is a 4 by 4 or a matrix of order 4. And if you are wondering about the entries on the diagonal, where are they? Well, they're right here. So 1 is the A11 entry, -1 is the A22 entry, and 7 is the A33 entries. And finally, that 0 here is the entry on the fourth row, fourth column, so the A44 entry. And here, it's important to notice that there's only one diagonal, so you are not using geometry here anymore. So only the entries where the row number and the column number are diagonal elements. All right, so for this first section, that's it. That's all. Bye bye.